So we have discussed mixed Nash equilibria and their existence. Let us now talk a bit more in detail about how we can find Nash equilibria, at least in simple cases, and which properties they have. So you see the photos, by the way, of John Nash, who is responsible for defining Nash equilibria and for proving their existence non-constructively, and it's impossible in general to constructively prove it. Up to some assumptions. And John von Neumann, who is responsible for general game theory and mostly for zero-sum games, which we are going to discuss too, as a particular case. So, Nash equilibria are the most famous solution concepts, and despite being so famous, despite being widely studied for quite some time already, about 69 years at least, since their since their formal introduction by Nash and proving that they always exist for a mixed extension of a finite game. We can't say much in general. Besides that, it always exists in a mixed extension of a finite game and other existence results, similar existence results, which we don't study, but which also are non-constructive, like Glicksberg's theorem. So there is not much known about their properties. By the way, even the description in the film A Beautiful Mind is wrong. Anyway, that's the reason probably that much research studies concrete classes of games, where we do know more about the structure of the equilibria. And now we are going to take a look at some simple cases of this study of Nash equilibria. So first we're going to look at constant sum games. We looked at them already, and now we are going to return, having proven that Nash equilibria always exists in the mixed extension of a finite game. We're going to both look at the theory and at some examples. Then we will return to the potential games, where we proved that even a Nash equilibrium in pure strategies always exists. And then we are going to talk about general properties of Nash equilibria and general examples. And finally, we will look at two very important games, concrete classes of games. One is atomic routine games. So it's the game where players choose a concrete path through which they want to go. Atomic means that you assume you have a finite number of players who each of which controls a non-negligible part of the traffic, unlike the case when we have infinitely many players with infinitesimally little traffic each. And in the case of atomic routine games, we're going to look at the efficiency. That's the famous result of Tardosh and Rovgarden. And then we're going to look at the network construction games at a very simple case, and also we're going to look at the efficiency of those games. So not just that you have an equilibrium, but what can we promise about the, let's say, worse equilibrium from the point of view of the social welfare. So let us go to constant sum games. And I remind you that constant sum game is a game of two players where there's a constant such that the sum of the utilities is equivalent to that constant. So it's constantly that value. And zero sum is a particular case when the sum is zero. So examples include matching pennies, chess, rock, paper, scissors, and the definitions also of max minimizer are important. So the max minimizer of a player is a value such that the minimum value of that player when the other player tries to play as bad for me as possible for him. So when the other player plays as bad for me as possible, and while I know that, I'm trying to maximize my value, so it's max min, and each player has his own max min. And we prove the following important theorem, basic theorem, that given a constant sum game, where the sum of the utilities is C, first of all, if you have we have a Nash equilibrium, which we don't know, we don't have to have it always. For example, in matching pennies and rock paper scissors, we don't have a Nash equilibrium. In chess, we do. We don't know which it is, but we know that we do. We will prove it in the future. So if you have a Nash equilibrium x star y star, then x is a max minimizer of player 1, y is a max minimizer of player 2, and the maximum of the minimum of player 1 is equal to minimum of the maximum of player 1. So the order does not matter. In general, that is not the case. In order, max min is at most min max. But if we have a Nash equilibrium, then they're exactly, and their value is also equal to the value of that player in the equilibrium. In this concrete equilibrium we looked at, and that implies in particular that all the equilibria have the same utilities. So if you have an equilibrium, then we have this equality, and then the equilibrium strategy have to be the max minimizers of the respective players. And the other way around, if we have this equality that max min is equal to min max, so that when player 1 maximizes, given that the other player first minimizes, it's the same as the other player minimizes given that the player 1 maximizes. And so if that, the other direction is that if that equality holds, this equality, let me, yes. And if we take a max minimizer for player 1 and a max minimizer for player 2, then those constitute a Nash equilibrium. So that equality basically characterizes the fact that we have a Nash equilibrium, and when we do, then it's exactly the max minimizers of the players. Now that's in general, and in general we don't know we have a Nash equilibrium, but from this theorem we can conclude the following about constant sum games, which are finite in about the mixed extensions of finite constant sum games. So since a constant sum game is necessarily also constant sum with the same constant, when we look at its mixed extension, because linear combinations of the same value will be the same value, I mean convex combinations of the same value will be the same value, the above theorem can be applied to the mixed extension, where we know that Nash equilibrium always exists, and then we are going to give the following. So given a finite constant sum game G, then for each max minimizer P star of player 1 and max minimizer Q star of player 2 in the mixed extension, so we are looking at the mixed extension, they have to constitute a mixed Nash equilibrium. And in that mixed extension, max min is equal to min max. So when the first player maximizes, given the second minimizes, that's the same value as the first player first maximizes and then the second player minimizes. And that's also the value of the first player in any equilibrium. So basically we simply applied the theorem we just cited for the case of a mixed extension, or the mixed extension of a finite constant sum game. And the only thing we need to prove is that the maxima and the minima are at 10. Since here the sets are infinite. But that follows from the compactness of the sets of the mixed strategies for finite games, and from the continuity of the expectations UI and of the maxima and minima. as maximum and minimum of continuous function. So eventually we have a continuous function over a compact set, and therefore we have maximum and minimum. It attains its extremum. Okay, that's the main thing, and also, so basically, that's what we have proven. And one is, I remind that one of the thing we defined is the value, and we said that when you have maximum of a minimum of a value is equal to the minimum of maximum, then we call this common utility value the value of the game. In the case of the mixed extension of a finite game, this mixed extension always has a value, because the maximum of the minimum is always equal to the minimum of the maximum, because we know that the mixed extension always has an Nash equilibrium. Okay, so we simply can ask what is the value. And before we go to look at examples, let us look, I think, at the last statement, and that's the following. We saw in the lesson about zero-sum games, or in constant sum games in general, that given a constant sum game G, the maximum of the minimum of player 2 is C minus the minimum of the maximum of player 1. So max min of one is minimum of min max of the other one. And also, not only the values are equal, but the arguments which achieve those max min and min max are the same. Therefore, taking the max minimizer of player 1, which we need if we want to find those mixed Nash equilibria, is equivalent to taking min maximizer of player 2, and the max minimizer of player 2 is equivalent to min maximizer of player 1. That's quite intuitive. I simply mentioned it formally. And now let us look at some examples. So let us look at the following game. I call it election game. It's not the election game we saw before, but it's also another election game that we have an incumbent president. So let's call that guy 1. And that guy, before the elections, that guy decides whether to set the taxes on high or a low value. Now the opposition leader can only influence the situation by publishing intimate pictures of player 1 or not. So the incumbent, in the matrix I denote him by I, chooses between high and low taxes, and the second guy, the opposition leader, can choose between publishing P and non-publishing NP the pictures of player 1. So the story is that people don't like high taxes. At least that's not a popular measure. So if there is nothing else besides the taxes, if the second guy, the opposition leader, does not publish anything, then setting taxes on high gives the guy who sets them on high a lower value relatively to setting them on low. And actually, since people don't like losing more than they like winning, as Kahneman says in his book, we even define the minus when the taxes are high to be -2, while the plus when the taxes are low is only +1. And the second play is always the minimum of the first one, because they are two candidates, so if one gains, the other one loses. Now, however, if the second player does publish the intimate pictures of player 1, then people get a bit emotional, and then player 1 needs to distract people, the people who elect him, by indeed actually making something they're going to think about more. So here high taxes can only help him because they're going to distract the electorate from thinking about those intimate pictures. So if the second player published the pictures, then we assume that high taxes actually benefit the incumbent guy, and that's one relatively to low taxes, which actually give him -1. And as I said, the other guy is always the minimum of the first guy. It's a zero-sum game. So first of all, there is no Nash equilibrium, and we can simply check that in every place we can move. There is at least one player who can move to the other, who can unilaterally improve her utility by moving. For example, if players choose high and publish, then the second player can choose non-publish and thereby increase her utility from -1 to 2. If the players are here, high and non-published, then the first player can choose low and thereby increase her utility from -2 to 1. If the players are here, so low and non-published, then the second player can choose publish and increase her utility from -1 to 1. And if the players choose low and publish, then the first player can choose high and increase her utility from -1 to 1. So there is no Nash equilibrium, and besides this direct check, we can also simply conclude this by the theorem that minimum of the maximum should be equal to maximum of the minimum, while here the minimum of the maximum is -1. Excuse me, maximum of the minimum is -1, while the minimum of maximum is 1. So that's another way to see that there is no Nash equilibrium using that characterization. But we know that we always have a Nash equilibrium in the mixed extension because it's a finite game. So let us find all the mixed Nash equilibria. So first, we're going to find them using the properties of a constant sum game. We can also find them using the properties of mixed Nash equilibria, but first we're going to use the properties of that. It's not just any mixed extension of a finite game, but it's a mixed extension of a finite zero-sum game. Because in this game, in zero-sum game, we know that a profile is a mixed Nash equilibrium if and only if it's a max-min of the corresponding player. So I need to go to each player and look what is the max-min of that player. So for player 1, let us denote her strategy that she chooses P with a high taxes with probability P and low taxes with probability 1 minus P, and player 2 chooses publishing with probability Q and non-publishing with probability 1 minus Q. So these are the functions based let me think how to explain it. Okay, based on the P of the first player, her utility will be described either 3P minus 1, because it's going to be minus 1 it's going to be one